Before we start proving the refinement model M2 being valid, let's recap what we have got so far. So we got the constant D that has been inherited from the initial M0, the most abstract model. And we got a new carrier set that we just introduced to M2, which is about the color for the traffic lights. And we got the associated axiom for the constants. And we got the 5 variables over here, A, B, and C from the abstract model M1, and also MLTL that we just introduced to M2. And remember what this refinement scheme is called. Superposition. Just remember that. Don't forget. And also we got the typing constraint, kind of invariance, and also we got the so-called conditional invariance to really constrain about the 5 variables. And it is called conditional because if this particular constraint is actually true, that would imply the consequence or the goal is actually true. That's something we derived together as exercises. Make sure you understand exactly how we did it. And we got 6 events over here. You can read it in this particular order. If you just recall what we did earlier, remember we talked about this diagram over here, and then can label the sequence in which the events may occur. You can see number 1, number 2, number 3, number 4, number 5, and number 6. And that somehow the order was kind of implicit on the slides. Let me show to you. Let me recap again. The traffic lights between the main lane and the bridge should be turned green first. And then the driver should be able to exit from the main lane accordingly. And then the driver, or the car, moving from the bridge into the island, it will be represented by ILN. And then the island traffic light should be turned green before the driver who actually want to go back to the mainland can actually go out of the island, right? And then eventually the car can actually go back to the mainland. So these are the events that are supposed to occur in this such sequence. And very quickly, let me see if there's anything else we need to mention. And look at ML out over here. For example, you can see the guard for ML out over here. That one there is really from the driver's perspective, meaning that the driver simply just follow the traffic lights, as opposed to in order for that corresponding traffic light to really turn green. So these are the global counter constraint that should be satisfied. More precisely, in order for you to turn the traffic light on the main lane side to be green, you want to make sure there's no opposite traffic, and also the cars are limited. So these are the constraints that we spoke about earlier. Symmetrically, if you want to turn the traffic light on the island side to be green, you want to make sure there's no opposite traffic, and also there's at least one car on the island to actually exit from there. And there are 2 constraints which I didn't quite mention in the earlier notes. Let me do it now. You want to make sure in order to turn the light to be green, it should be already red at the moment. It should not be already green, because this doesn't make sense for the light to be already green. You want to turn it to be green again. So that's why we got this constraint over here. All right, let me show to you very quickly. You want to make sure if I want to turn this particular traffic light to be green, it better be at the moment just red. Symmetrically, in order to turn this traffic light to be green, it better be that it's at the moment red rather than green, right? You cannot turn you don't really want to turn a green traffic light green again. Let's now write it down. So what we should write over here was MLTL. Before you turn that to be green, you want to make sure at the moment it's actually red. Symmetrically, in order for you to turn the ILTL on the island side to be green, at the moment it better be the opposite states, which will be, let's say ILTL should be equal to red. So these are the 2 constraints that should have been put there, but I forgot. Now you can also fix your notes if necessary. Let's go back. And if you look at the ML out and also IL out, so these 2 events will not be very straightforward, simply just the driver following the direction of the traffic light. So again, it's very important, as we explained before, you should really know about the guards between the ML out from the driver's perspective and also MLTL green from the global equipment's perspective. So these are quite important, and the relationship between IL out and also ILTL green is kind of analogous, similar. Okay, what about ILN and also MLN? So these 2 events, even though they are so-called old events that already exist in the abstract model M1, however, we didn't have the need to refine them for the following reason. If you take a look at the diagram over here, ILN over here, and also MLN. So these two events are not really affected by the new variables traffic light that we introduced. So that's why they can remain the way they are, as opposed backing M1, the abstract model. So that's why when we proved the invariant preservation, we didn't really have to touch them because they didn't affect anything about the new variables, ILTL and also MLTL. That's something important to note as well. Let's now go over some bullet points and then we'll formulate the invariant preservation. So for this part, it's just standard about proving the refinement. Nothing's new. So I think it's really good to exercise the whole workflow again. And I'll leave many parts as exercises for you this time. So recall the invariant preservation rule for refinements over here, right? So we need to put the axiom, the abstract invariance, the concrete invariance, and the concrete guards for the events that we're talking about. And also, this will be the concrete invariance with the effects of the abstract and also concrete events, right? So this will be something you have to make sure how to do the substitution. This is something that we did earlier, also for the first refinement M1. So that's something I'll leave to you. But I'll still do one exercise with you. But the other ones will be up to you. If you still got trouble instantiating this particular concrete invariant in the post states, reach out to me. Right? How many sequence to be proved? As far as the model right now is concerned, I'll give you some heads up. Later on, we'll find the need to split some of the events into two, in which case we're going to increase the number of events. But we'll worry about that when we get there. For now, we got 1, 2, 3, 4, 5, 6. We got 6 events over here. In that case, we really need to, in theory, we need to formulate 6 times 4 sequence, right? Including the ILN and also MLN, even though the proof will be quite straightforward because they didn't really impact the traffic lights, but you still need to formulate the sequence if you're asked to prove it. So the number of concrete invariants will be 1, 2, 3, 4, 5, 6. And how many concrete invariants do we have? We have 4. You can see 1, 2, 3, 4. Later in the lecture, we'll also introduce more invariants into the context. In that case, you definitely have to update this number over here. But for now, I just am reminding you about this formula. So as we add either more invariants or we add more events, in that case, you should always remember to keep this number up to date, right? That may not be something I will always remind you. You just remember. And we will now discuss 2 sequences over here. So one will be specific to ML out over here, and the other one will be specific to IL out over here. So these are the 2 old events that have been refined for their guards over here. That's something we'd like to see, whether they can preserve the invariance. Specifically, we want to see invariant number 4 over here for ML out, and we want to see invariant 3 over here for IL out. That's what we like to see. And let's now switch to see how this invariant condition can be formulated. We'll do one of them. The other one will be your exercise. Let's take a look. And just very quickly to set up the context so you will also be able to do the exercise later. We have the abstract model, in this case the first refinement M1. And we have the concrete model, in this case the second refinement M2. And I'm not including the axioms and the constant. You can definitely look them up back in the notes or the slides. But we got the variables over here, and we got a superposition, the additional 2 variables, and we got invariance, and we got the 2 events for which we want to formulate the invariant preservation. And the exercise for you will be to formulate this particular invariant preservation sequence for the proof obligation. That'll be your exercise to do. Let me now go over with you very quickly about this particular one. For ML out, invariant 2,4 over here, and about invariant preservation, for which you can refer to this formula that we spoke about earlier. Very quickly, okay. And for this part over here, okay, this part is just about the axiom and the constant, right? So this part here is not really included in the iPad notes, but you can definitely look them up from the earlier notes. So that's just about the axiom. And you also have to put in the abstract invariance from model 1. So in that case, the abstract invariant would be model 0 and model 1. Let me show to you just a moment, but let me just put it here. So this part over here is the abstract invariance. Abstract invariance. And as you can see, the model number over here is, you can see 0 and also 1. The earlier two models, M0 and 1, they ought to be all included because they might be useful for you to prove the sequence, the goal of the sequence. And we also got concrete invariance. And for the concrete invariant, that should be straightforward. For the moment, we got 4. Right? So these will be the concrete invariants over here. So this part over here is the concrete invariance, all the 4. And don't forget, we also got to put a concrete guard. And for the concrete guard, let me put in purple. So this one over here will be the concrete guards for ML out. So this will be the concrete guard of the events that we're talking about is ML out. So that's why it should appear there, right? Okay, if I can just write a little bit better, I should do it. Okay, that's good enough. And you can see ML out, that's exactly the concrete guard we are speaking about. And this part over here, I found that some of you are, during my office hour or the Q&A, you're still having some trouble substituting the post-states version of the concrete invariant. Let's do it again. I think it's rather important. You'll definitely be expected to do such a thing later in the assessment. How did we work out exactly what to put over here? The principle is actually quite easy, because according to the rule over here, this basically is just the post-state version of the invariance. That's the principle. So here we're talking about invariant 2,4. So what we should do is, I can definitely do it better. So invariant 2,4. Invariant 2,4 is actually over here. And first of all, let's put the post-state version for that. Okay, let me try to work out the logic together with you. Let me say star over here. I put a star over here. The post-state version will be ILTL prime equals green. All the variables should be primed. Implies B prime larger than 0 and A prime equals 0. So that will be the post-state version. However, you cannot put any prime variables in the actual sequence. It will not be valid. What you should do is you should really do any substitution whenever possible. Let's take a look. In the case of the ML out, what's the before-after predicates? Remember, we talked about the before-after predicates, and we say that you only mention about the variables that will be modified. Anything else that's not really mentioned is not modified. So what's really missing here? We're only mentioning about A, meaning that B, C, MLTL, ILTL, they all stay the same. Implicitly, so this would be the before-after predicate. Before-after predicate should be A prime is equal to A plus 1, and B prime is equal to B, C prime is equal to C, and MLTL prime is equal to MLTL, and also ILTL prime is equal to ILTL. So these are all the stuff that we spoke about before. I'm just reviewing them. Just make sure you're okay. And given this, how can we replace them? So ILTL prime over here is simply just ILTL. It doesn't change. So it will be the same value as the before states. Green here is just a constant, so we don't change it. B prime over here, according to before after predicate, would just be equal to B. What about A prime over here? It would be A plus 1. Right? So that's why you will see exactly this particular invariant over here. That's what you will see. ILTL equals green implies B larger than 0 and A plus 1 equals 0. B larger than 0 and A plus 1 equal to 0. That is very important for you to actually get this right. Alright, exercise time for you. Before you move on to the next part, in which we're going to start doing the proofs for the invariant preservation, I would suggest you try to specify this invariant as well for the proof obligation. That'll be for IL out, for invariant condition number 3, and also for invariant preservation. Alright, so do the exercise before you move on to the next part.